Okay, let's get into this. Have you ever looked at a really dramatic landscape? Maybe towering cliffs or deep valleys or even those uh, strange sort of pockmarked hills you see in some places,
Hmm.
and just wonder how on earth did they get that way? We tend to think of rock as, well, solid, right? Permanent, unchanging.
Yeah, that's the common perception. Solid as a rock, as they say.
Exactly. But landscapes, they're actually anything but static. They're constantly being sculpted really slowly, um, relentlessly even, by forces we often can't even see day to day.
Right. Forces that have immense power over geological time. Water is a big one.
Precisely. And today we're doing a deep dive into one of the most, I think, fascinating examples of this kind of shaping,
Yeah.
the incredible world of limestone and chalk landforms.
Often called karst regions, yeah.
Karst regions, that's the term.
And what's really remarkable about these places is how something so common, just water, interacting with a specific type of rock, limestone, can create scenery that's just so unique. Sometimes really bizarre, even.
It really is. It's
Yeah.
like a testament to the power of those persistent, slow-acting geological processes you mentioned.
Absolutely.
And our guide for digging into this world of soluble rock and hidden water is an excerpt from a classic geography text that kind of lays out the basic science and walks us through the key features that make these places so distinctive.
Mm-hmm. So our mission here in this deep dive is really to unpack that source material. We want to pull out the most important sort of nuggets of knowledge
Right.
and help you understand not just what these features are, the names and shapes, but really how they form and maybe why they matter.
Think of it as getting like a backstage pass to the geological theater that's happening quietly under the surface, helping you appreciate the forces that shaped these parts of our planet.
That's a good way to put it. A geological backstage pass.
Because I find this topic genuinely, well, mind-blowing.
Hmm.
The idea that a simple rock and just plain old water, okay, slightly altered water, as we'll see, can conjure up things like underground rivers, caves filled with stone icicles, or surfaces that look like giant broken pavements.
Yeah.
It really challenges your whole perception of how solid the Earth actually is, doesn't it? I'm really looking forward to digging into the specifics here.
It's a fantastic subject, full of surprises, and the transformations are quite profound, really.
Okay, so let's start right at the beginning.
Mm.
The absolute foundation, the rocks themselves. What are limestone and chalk? The source tells us they're sedimentary rocks. Now, we hear that term a lot in geology, sedimentary. But what does it specifically mean here? Why is that origin so important for understanding these landscapes?
Right. Good place to start. So sedimentary rocks, they're formed over, well, vast stretches of time, basically through the accumulation and then cementation of material. Often this happens at the bottom of bodies of water, like seas or lakes.
Accumulation, okay, like layers building up.
Exactly. And the source clarifies that limestone and chalk are largely derived from the accumulation of marine organisms. We're talking specifically things like corals and shells settling on ancient seabeds.
Wow, okay, so ancient sea life.
Millions of years ago, yeah. Imagine shallow, warm seas just teeming with creatures building skeletons and shells out of calcium carbonate. As they died, their hard parts drifted down, settled on the seafloor, layer upon layer upon layer.
Okay.
And then over immense periods, the sheer weight of all those overlying layers, plus mineral-rich water circulating through them, compacted it all and cemented the material together into rock.
So they're essentially compacted, fossilized piles of ancient sea life. That makes them sound, well, maybe less solid in a way, more organic than something like granite, maybe.
Precisely. That biological origin is absolutely key to their composition. The main ingredient, the fundamental building block in both limestone and chalk, is calcium carbonate. The source points out this often occurs in the mineral form called calcite.
Calcite, okay.
You can also find dolomite mixed in sometimes. That's calcium magnesium carbonate. And chalk. Chalk is singled out by the source as being a very pure form of limestone.
Very pure. That explains the color.
Yeah, that purity is why it's typically that bright, striking white color we associate with chalk cliffs, for instance. And it's also why it's significantly softer and more easily crumbled, more friable than many other cubes of limestone.
Okay, so fundamental building block,
Mm.
calcium carbonate, often from ancient shells compacted into rock.
Yeah.
Chalk is the pure, soft variety. But the absolute most crucial property, the
Yeah.
one the source really hammers home, the one that everything else flows from,
Hmm.
is that limestone is soluble in water.
Yes.
This is where the magic happens, right? Or maybe the chemical reaction?
This is absolutely the linchpin. Most common rocks, think granite or basalt, they're relatively impermeable. They're pretty resistant to chemical dissolution by water. They might wear down physically, erosion, but they don't just dissolve away. Limestone is fundamentally different. That calcium carbonate composition makes it susceptible to being dissolved by even slightly acidic water.
But the source is specific. It says soluble in rainwater, which with carbon dioxide from the air forms a weak acid. So it's not just pure HO doing the work. The water has picked something up first.
Exactly. That's the critical nuance there. Pure water, HO, is pretty neutral, pH around 7, but as rainwater falls through the Earth's atmosphere, it naturally absorbs small amounts of carbon dioxide, CoA.
For the air.
From the air, yeah. This HOO dissolves in the water, and it forms a weak solution of carbonic acid, HEO. It's actually the same weak acid that gives fizzy drinks their slight tang.
Okay, like soda water, but much weaker.
Much, much weaker, but effective over time. This carbonic acid is the active agent. So when this slightly acidic rainwater comes into contact with the calcium carbonate kako in the limestone, a chemical reaction happens.
Okay.
Basically, the calcium carbonate reacts with the carbonic acid in the water, and it forms something called calcium bicarbonate. And the key thing is, calcium bicarbonate is soluble in water. It can be carried away in solution.
So the slightly acidic rainwater literally eats away at the rock, molecule by molecule almost.
That's a pretty good way to visualize it, yeah. At a fundamental level, it's a constant, slow chemical weathering process. The rock isn't just being worn down physically, it's literally being dissolved and carried away in liquid form.
Wow.
And the source gives us a great bit of context here. It mentions a region in what was then Yugoslavia called Karst.
Karst, okay.
It says this area has such particularly well-developed topography shaped by this very dissolution process that it actually gave the entire category of landscapes its name. So we talk about karst topography because of the karst region.
That's fascinating. So the name comes directly from a place where these features are just spectacularly displayed. Okay, so we've got the ingredients. Soluble rock made of ancient shells, and this slightly acidic rainwater as the sculptor. Let's dive into the main event now. What does this interaction actually create? What are the characteristic features we see above ground in these karst regions?
Right. So when you look at a typical well-developed karst region, the source describes the general landscape appearance as often being quite bleak, maybe bare.
Bleak, okay.
Yeah, not lush and green necessarily. You might see areas broken up by steep slopes. The source uses the word precipitous, almost cliff-like in places. It's usually not a landscape of gentle, soil-rich slopes and obvious flowing rivers, though chalk areas can be a bit different, as we'll get to.
And one of the most striking things, often quite confusing about these landscapes, as the source highlights, is the general absence of surface drainage. You look around, maybe even after rain, and there are no permanent streams or rivers flowing across the land.
Exactly.
Where does the water go?
Yeah.
It's like it vanishes.
That's really the defining characteristic of karst, and it's a direct result of the rock being soluble and often quite porous or well-jointed. The water simply doesn't stay on the surface for long. It finds pathways into the rock and travels underground instead. The whole landscape is drained internally from below.
So you might see a stream appear for a little while, maybe flowing down a hillside, and then it just, poof, gone.
Exactly that. The source talks about ephemeral streams. These are streams that might flow over the surface for just a short distance, perhaps where there's a thin layer of less permeable soil or some sediment cover.
Okay.
But as soon as they encounter the bare limestone, or maybe just thinly covered limestone, they disappear abruptly. They literally sink into the rock through fissures, cracks, swallow holes, joining that subterranean drainage system.
Swallowed whole, you said.
Pretty much, yeah, the smaller ones anyway. For larger, more established streams, they might manage to cut sort of shallow courses along weaknesses in the rock before they eventually find a way underground too, but the little ones are just gone.
And this underground redirection of water, it leads directly to another classic karst feature the source mentions, dry valleys. These are valleys that look exactly like they were carved by a river, right? They've got the shape, the floor, the slopes, but they're dry, often completely empty of water.
That's right. These dry valleys are essentially relics. They're remnants of older surface drainage systems. What happened is, over geological time, as the underlying limestone was being dissolved and these underground cave networks started developing,
Right.
The surface streams that originally flowed in those valleys found it was actually easier or faster to disappear underground higher up in their course. They found a shortcut down.
So the river basically abandoned its old surface channel.
Exactly. It took an underground route instead, leaving its former valley high and dry. They're like fossilized riverbeds on a landscape scale.
Ghost rivers and fossil valleys. It really paints a picture. Okay, so if all this water is disappearing underground, where does it eventually come out? It can't just stay down there forever, can it?
No, absolutely not. It has to go somewhere. And that's where you get what's called resurgence.
Resurgence, okay.
The source explains that this underground water flows through these complex networks of caves and passages, always moving downwards due to gravity, following the easiest path. Eventually, it reaches a point where it hits an impermeable layer of rock underneath the limestone.
Something it can't dissolve.
Exactly, a layer it can't dissolve or easily penetrate. So when its downward path is blocked, the water is forced to flow horizontally, sideways, until it finds an outlet back onto the surface. This often happens at the edge of the limestone area, or maybe where a fault brings the impermeable layer up or a valley cuts down to it. The water emerges, sometimes quite dramatically, as a powerful spring or maybe a group of springs, and that exit point is called a resurgence.
Okay, so water sinks down through features like swallow holes, travels underground, and pops back out at resurgences. It's like a hidden plumbing system beneath our feet.
A natural hidden plumbing system, yeah.
The source also really emphasizes the importance of the rock being well-jointed. It mentions vertical joints and horizontal bedding planes. Why are these weaknesses, these cracks and layers, so critical for karst to develop?
Think of the limestone bedrock. It's not usually a perfect, seamless block, right? It has natural weaknesses within it. Joints are basically fractures or cracks in the rock. They often run vertically or near vertically. They might form from tectonic stresses, the earth moving, or even just from the rock cooling and contracting way back when it formed.
Okay, natural cracks.
And bedding planes are the horizontal surfaces. They separate the different layers of sediment that were originally deposited when the rock was forming on the seabed, so they represent the boundaries between those ancient layers.
Got it. Joints vertical, bedding planes horizontal.
Generally speaking, yeah. And these joints and bedding planes are the crucial pre-existing pathways. They're the initial routes where that slightly acidic rainwater can first start to penetrate into the main body of the rock.
So the water finds these natural weaknesses to get started. It doesn't have to dissolve its way in from scratch everywhere.
Exactly. They provide the initial entry points, the lines of attack, if you like. And once that slightly acidic water gets into these joints and bedding planes, that dissolution process we talked about really kicks into high gear along those pathways.
Ah, so it concentrates the dissolving power.
Precisely. The water starts dissolving the calcium carbonate along the walls of these joints and bedding planes. And as it dissolves the rock, the cracks get wider and wider. This widening process is absolutely fundamental to how basically all karst features develop, starting right there at the surface.
And that process, widening those joints specifically, leads us straight to one of the most visually unique surface features. The source references it with figure 64, limestone pavement. Can you describe what that actually looks like?
Yeah, limestone pavement is really distinctive. It looks almost artificial sometimes, like a massive, deliberately laid but now broken pavement made of stone slabs. It typically forms where a horizontal bedding plane of limestone is exposed right at the surface, maybe scraped clean by glaciers in the past.
Okay.
And the surface is divided into these individual, often flat-topped blocks, separated by deep fissures or cracks. The source calls the isolated blocks clints.
Clints, like paving stone.
Yeah, and the deep, widened fissures between the clints are called grikes.
Clints and grikes, got it. So it's the blocks, clints, separated by the gaps, grikes. How does that specific pattern actually develop? It looks so regular sometimes.
It's a direct result of that dissolution process being concentrated along the pre-existing joints in the rock. Rainwater collects on the flat surface of the exposed bedding plane on the clints, and then it naturally runs off and seeps down into the joints, the lines between them. And that slightly acidic water preferentially dissolves the rock along the edges and walls of these joints. So over vast periods of time, this chemical weathering widens and deepens those original tight joints into these substantial gaps, the grikes. The clints are simply the sections of the original bedrock left standing in between these enlarged fissures.
Ah, okay.
Yeah.
So the grikes are where the dissolving action is really focused.
Exactly. The source notes that this process, Widening the cracks into these trenches or grikes is often the most significant initial feature to develop on the surface of bare limestone. It sets the stage for everything else.
It makes perfect sense. The acidic rain focuses its energy on those weak points, the joints, and just carves them out deeper and wider over time. And while the clints are the visible pavement stones, the real action, the water disappearing underground, is happening down in those grikes.
And sometimes at specific points along those grikes or where joints intersect.
Right. Which brings us to the next feature the source highlights, also referencing figure 65. Swallow holes, or sinkholes. These seem even more dramatic places where the surface just seems to, well, give way or funnel downwards.
Yes, swallow holes or sinkholes, as they're very commonly known, are perhaps the most iconic visual representation of water actively going underground in karst areas. They're basically depressions on the surface. They can range hugely in size, from small funnels just a meter or two across, maybe hidden in the grass, to much larger basins.
And their whole purpose is to channel water down.
Exactly. They are points where surface water, rainwater running off the land, or sometimes even entire streams, as we discussed, directly sinks into the limestone bedrock and disappears into that underground drainage system.
And their formation is also primarily by that solution action, dissolving the rock.
Exactly. The source explicitly states they are formed by solution action. It involves that continuous process of slightly acidic water dissolving the limestone. It often starts around a specific point, maybe a major joint intersection, or a point where the rock is perhaps slightly weaker or more fractured.
Okay.
As water concentrates there and dissolves the rock downwards, it naturally creates a sort of funnel-shaped depression. And that shape then becomes even more efficient at channeling more water underground to that same point.
So it's a self-reinforcing process.
Very much so, yeah.
Okay.
It's continuous. The more water goes down, the more rock dissolves, the bigger and deeper the hole can potentially get over time.
The source mentions Gaping Gill in Yorkshire as an example.
Yeah.
That name alone sounds pretty formidable.
Gaping Gill is a classic, and yes, a very dramatic example. It's one of Britain's most famous sinkholes, or potholes as they're often called there. It's where a surface stream, the Fellbeck, literally plunges into this massive shaft. Yeah, it drops vertically over 100 meters, that's over 300 feet, straight down into one of Britain's largest underground cave chambers. It perfectly illustrates that direct connection between a surface feature and the vast subterranean world beneath.
Wow, 100 meters straight down. That's incredible. The source also notes that these smaller sinkholes can sometimes coalesce, merge together.
Yes, exactly. As multiple adjacent swallow holes or sinkholes expand through continued solution, their rims can eventually meet and merge. When this happens, they create a larger, often shallower compound depression. The source calls this feature a doline.
A doline. Okay, so bigger than a single sinkhole.
Right. Think of it as several funnels sort of joining up at the top to form a broader bowl shape. And then if several dolines coalesce,
They get even bigger.
they get even bigger. An uvala is a yet larger, more complex depression formed by the merging of multiple dolines. The source notes uvalas can be quite extensive, sometimes stretching for miles across. So you see this clear progression in scale and complexity, from individual sinkholes merging into dolines, which then merge into even larger uvalas. And it's all fundamentally driven by the expansion and coalescence of these surface dissolution features.
So the surface landscape just becomes increasingly pitted and hollowed out over time as the underlying rock dissolves away. Are there any features described that are even larger than uvalas?
Yes, the source goes on to describe poljes, Poljes. These are very large, often distinctively flat-floored depressions within the karst landscape. They can be vast. The source mentions potentially hundreds of square miles in size.
Hundreds of square miles, so like huge basins.
Exactly, huge basins or valleys. Now, the source points out that while solution is definitely involved in shaping them, their formation is often partly due to structural controls in the bedrock, like major faults. These faults can create large, down-dropped blocks or gribbons within the limestone region, forming the initial basin.
So geology gives it the initial shape, then water modifies it.
Pretty much. And because they're large depressions, poljes tend to collect drainage from the surrounding higher karst terrain. This means they can sometimes contain temporary lakes, especially during rainy seasons. Their flat floors can also accumulate alluvial deposits, silt and clay washed in, which can make them potentially more fertile and amenable to agriculture than the really rocky karst areas surrounding them.
Okay, so poljas are like the large-scale valleys or plains within a broader karst landscape, potentially a bit more habitable. Now, the source also mentions limestone gorges, referencing figure 65 again, along with the sinkholes. How do you get these deep, steep-sided gorges in a landscape where the water generally prefers to disappear underground? It seems counterintuitive.
It does seem a bit counterintuitive at first, doesn't it? But this is where the underground network becomes directly responsible for shaping the surface in a really dramatic way. The source explains that limestone gorges are typically created when the roof of a large underground tunnel or a cave passage collapses.
The roof collapses.
Yeah, so imagine over long periods, water flowing through a subterranean passage, dissolving and eroding the rock, making the passage wider and higher. The roof rock above this growing void can become progressively thinner and more unstable.
Right.
Eventually, it can no longer support the weight of the rock or soil above it, and it collapses downwards into the passage below. This collapse creates a deep, steep-sided valley or gorge on the surface that directly follows the line of the former underground passage.
Wow. So a gorge isn't necessarily always carved by a surface river slowly eroding downwards. It can actually be the scar left behind when a massive cave system collapses. That's an incredible thought.
It really is. And the source gives Cheddar Gorge in England as a prime example.
Cheddar Gorge, yeah, famous place.
It's this magnificent, deep gorge cut through the Mendip Hills limestone. And the geological evidence strongly suggests it was formed primarily by exactly this process. The collapse of massive underground caverns and tunnels, likely aided by meltwater during ice ages, rather than by simple surface river erosion in the conventional sense.
That's amazing.
It beautifully demonstrates how the processes happening in that hidden world beneath the surface can radically, and sometimes quite suddenly, transform the landscape we see above ground.
Okay, so we've journeyed across the karst surface now. We've seen how this interplay of soluble rock, slightly acidic water, joints, and just immense amounts of time creates these often bleak slopes, the disappearing streams, the dry valleys, those patterned limestone pavements, sinkholes of various sizes from tiny funnels to huge uvalas, vast polges, and these dramatic collapsed cave gorges.
A whole suite of unique landforms.
But as you've hinted, and as the gorge example shows, the real marvel, maybe, often lies unseen beneath the surface. So let's go underground now and explore the hidden world of karst features that the source describes.
Yes, absolutely. So subterranean realm is really where that dissolution process has been working most intensely, often for the longest time. It's all happening along those initial pathways, the joints and the bedding planes we talked about. As the water flows along these weaknesses underground, it just keeps dissolving the limestone, continuously widening those conduits.
And this is how the really extensive networks of caves and caverns get formed. It's not just isolated holes.
Precisely. The source states that the region beneath the surface becomes honeycombed with caves and caverns. This isn't just a few scattered holes here and there. In well-developed karst, it's often a complex, three-dimensional labyrinth.
Like a sponge.
Kind of like a rocky sponge, yeah. A network of interconnected tunnels, large chambers, vertical shafts, all following the preferred paths of groundwater flow through the rock mass. This extensive cave system is the direct result of that continuous dissolution of the limestone by the moving underground water over millennia.
And these underground spaces, they're far from empty, right?
Yeah.
They contain some truly spectacular, almost alien-looking formations. The source references figure 66 here, showing stalactites and stalagmites. Let's start with the ones hanging down from the ceiling stalactites. What exactly are they and how do they grow?
Right, stalactites, they're those sharp, slender, often tapering pinnacles that hang downwards from the roof of a cave. They look very much like rocky icicles, don't they?
They really do.
And their formation is this slow, beautiful chemical ballet. It starts with water that has trickled down through the limestone bedrock above the cave. As it passed through the rock, it absorbed that carbon dioxide, became slightly acidic, and dissolved a small amount of calcium carbonate, holding it in solution as calcium bicarbonate.
Okay, so it's carrying the dissolved rock.
Exactly. Now, when a droplet of this mineral-rich water reaches the airspace inside the cave, something happens. The air in the cave typically has a lower concentration of COs compared to the water itself. So some of that dissolved carbon dioxide slowly starts to escape from the water droplet back into the cave air, degassing, basically.
Like letting the fizz out of a soda, you said, but much, much slower.
Exactly the same principle, just incredibly slow. And when that coerce escapes, the chemical balance changes. The water can no longer hold as much dissolved calcium carbonate in solution as it did before. So a tiny, absolutely microscopic amount of solid calcium carbonate gets precipitated out of the solution. It gets deposited as a solid mineral right at the point where that water droplet is hanging on the cave roof.
Just a tiny bit from each drop.
A minuscule amount. And as successive drops form, hang there for a bit while degassing, and then finally fall, each one leaves behind another tiny ring or film of this deposited calcium carbonate, this calcite. Over thousands, tens of thousands, even millions of years, these tiny deposits build up, ring upon ring, growing downwards and outwards, forming the stalactite.
Growing literally drop by drop over eons. That's incredible patience from nature.
It really is. The source accurately describes their characteristic sharp, slender shape, which comes from the water running down the outside as it grows.
Okay, so stalactites hang tight to the ceiling. What about stalagmites? The source says they're the upward-growing features rising from the cave floor, and they're typically shorter, fatter, and more rounded. How do they form?
Stalagmites are essentially the floor-based counterparts, often forming directly below a dripping stalactite or just a drip point on the ceiling. So that water droplet, after initiating or adding to the stalactite's growth, or maybe just dripping directly from the roof, finally falls to the cave floor.
Okay.
Now, when it hits the floor, it still contains some dissolved calcium carbonate because the degassing process on the ceiling wasn't necessarily 100% efficient. When the drop hits the floor, it splashes and spreads out a little bit.
Spreads out more than it did hanging.
Yeah, it creates a thin film of water momentarily. And in that thin film, more Kiuros can escape into the cave air. Again, as the Kio leaves, more solid calcium carbonate is precipitated out of the water and deposited onto the cave floor.
But this time, the deposit builds upwards from the floor rather than hanging down.
Correct. And because the water spreads out more on impact compared to the concentrated drip point on the ceiling, the resulting deposit tends to be less focused, less linear. As subsequent drops fall in roughly the same spot over long periods, the deposited calcium carbonate builds up layer upon layer, growing upwards from the ground.
Ah, okay.
This spreading and sort of pooling of the water on the floor before evaporation often leads to stalagmites being generally shorter, wider, and having a more rounded or maybe conical shape compared to the slender, pointy stalactites above them.
So stalactites hang tight from the ceiling. Stalagmites might make it high from the floor. That's the classic way to remember them, isn't it?
That's the one. C for ceiling, G for ground. It works.
And the source also references figure 66 to show pillars. What are they?
Yes, a pillar, or a figure calls one example a calcite pillar, is basically the logical conclusion of this whole process when you have a stalactite growing down and a stalagmite growing up directly beneath it. And they're both growing for a very, very long time.
They meet in the middle.
Eventually, yeah. They meet and they fuse together. They form a continuous column of solid calcium carbonate, essentially calcite, connecting the cave floor directly to the cave ceiling. It's really a testament to the sheer duration and stability of the depositional process in that particular spot.
It really brings home the immense scale of geological time involved in forming these intricate features, doesn't it?
Yeah.
Drop by drop, molecule by molecule. The source lists some famous cave systems where these kinds of formations are particularly well displayed.
It does. It provides several examples that are world-renowned for their spectacular cave decorations, or speleothems, as they're technically called. It mentions the Batu Caves in Malaysia, known for their large chambers and Hindu shrines within them.
Okay.
Mammoth Caves in Kentucky, USA, which, besides having stunning formations, is also the longest-known cave system in the entire world, miles and miles of passages.
The longest, wow.
Yeah. Carlsbad Caverns in New Mexico, USA, which is famous for its absolutely massive underground chambers like the Big Room and just incredible diverse formations. And also Postojna Caves, which is in modern-day Slovenia, historically part of Yugoslavia, as mentioned in older texts. It's another very large, historically significant, and heavily decorated cave system.
So these are places where the conditions, the right type of limestone, enough water, stable conditions over long periods, were just perfect for both extensive cave development and the abundant deposition of these beautiful mineral formations.
Exactly. Prime examples of subterranean karst development.
Okay, so we've explored the rock itself, the dissolving process, the unique features above ground, and now the incredible sites hidden below in the caves. Zone out a bit now. Where in the world can you actually find these remarkable karst landscapes on a large scale? The source gives us a list of key regions.
It does. It names several significant global areas where limestone and chalk formations are extensive enough, and the conditions are right, for these characteristic features to develop prominently. The first one it lists, very fittingly, is northwest Yugoslavia.
The namesake region.
The namesake, yeah. Specifically mentioning the Dinaric Alps region. As we noted, this is the very area encompassing parts of modern-day Slovenia, Croatia, Bosnia and Herzegovina, Montenegro, Serbia, that gave the karst landscape type its name because it has such classic, well-studied examples.
So that's ground zero for karst studies, in a way. Where else?
Other regions mentioned include the Caucasus district of southern France, which is known for its rugged limestone plateaus and deep gorges. The Pennine region of Britain is listed,
Ah, yes.
which includes famous areas in northern England like the Yorkshire Dales and parts of Derbyshire. These are renowned for their limestone pavements, their caves, sinkholes or potholes, and dry valleys.
Yeah, definitely. If you've ever gone walking in the Yorkshire Dales, you've almost certainly walked over or past karst features. It's textbook territory there.
Absolutely. The source also highlights the Kentucky region of the United States, which makes sense given it's home to the vast Mammoth Cave system we just mentioned. That confirms its global significance as a karst area.
Right.
The Yucatan Peninsula of Mexico is another major example listed.
Ah, the Yucatan. Famous for its cenotes, right? Those natural sinkholes, often water-filled, that were so important to the Maya civilization. A perfect example of karst in a tropical setting.
Exactly right. Cenotes are essentially water-filled sinkholes or collapsed cave sections, classic karst. The cockpit country of Jamaica is also listed.
Cockpit country? What's that like?
It's characterized by a really unique landscape of steep-sided, rounded, conical hills separated by deep enclosed depressions or hollows. It's often described as looking like an egg carton from above, or like cockpits, hence the name. It's formed by intense dissolution of the limestone in a humid tropical climate.
Wow, egg carton terrain. That sounds unique.
It really is. And finally, the source includes the limestone hills of Perlis in Malaysia, which is another tropical example, known for steep, tower-like limestone hills rising dramatically from surrounding plains, often riddled with caves.
Okay, that's a pretty diverse list. Europe, North America, Central America, the Caribbean, Southeast Asia. It really shows that while the underlying geology having extensive limestone is absolutely key, the climate also plays a significant role. It influences things like the amount of rainfall driving the dissolution, the vegetation cover, maybe even the specific style of the landforms, like those Jamaican cockpits or the Yucatan cenotes.
Absolutely. Climate modulates the karst processes, but fundamentally, these are all areas where you have vast layers of soluble rock meeting sufficient water, and they've had enough geological time for these slow processes to really work their magic on a grand scale.
It's that specific convergence of geological and climatic conditions that allows this distinctive karst topography to develop so prominently.
Now, let's shift perspective slightly and think about what it's like to actually live on or in these landscapes. How does this unique geology impact human life and activities? The source seems to paint a somewhat challenging picture for typical karst regions.
It does, generally speaking. The source notes that human life can often be quite difficult in classic karst areas. One major issue is the soil. It's often very thin, maybe patchy, sometimes quite barren, forming only a pore layer directly on top of the hard bedrock.
Not great for farming then.
Not usually, no. And compounding that is the water issue. Because the rock is so porous or well-jointed and the water drains away so quickly underground, there's generally very little or sometimes no reliable surface water like rivers or lakes. And accessing the groundwater deep below can be difficult and expensive.
Right.
So this combination, lack of reliable surface water and often poor thin soils, makes traditional agriculture quite challenging. Settlement can be difficult too, and as a result, vegetation growth is often sparse in many temperate karst regions. You get that bleak look we mentioned earlier. So you wouldn't typically expect to find large, productive farms or densely populated cities situated right within the most intense karst areas. It sounds like the landscape itself presents some fundamental obstacles.
Not typically, no. The basic requirements for large-scale conventional agriculture and dense human settlement, things like fertile, deep soil, and easily accessible surface water, are often severely limited in these landscapes. However, the source does point out some important variations in human adaptations.
Okay, so it's not impossible everywhere.
Not impossible, and there are differences. For instance, the source notes that while many limestone areas are barren or rocky, chalk areas, particularly in temperate climates like southern England, can actually support good quality grass and short turf.
The chalk downs.
Exactly. Now, this isn't usually suitable for intensive arable farming, but it is very suitable for sheep grazing. And sheep farming has been a traditional and important land use on chalk downs for centuries.
Right. So chalk, despite being soluble limestone, offers slightly better conditions, at least for grazing animals. What about those tropical examples you mentioned earlier, like Perlis in Malaysia or maybe Jamaica? Are they just as challenging?
That's an important contrast the source highlights. Tropical limestone regions, like Perlis mentioned in the text, can surprisingly support quite luxuriant, dense vegetation.
Really?
Mm.
How does that work with the drainage?
Well, it's often because they receive extremely high amounts of rainfall throughout the year. So even though the water still drains away underground very quickly because the rock is permeable, the sheer volume of rainfall means there might be enough moisture available near the surface, at least temporarily, to support dense jungle or forest growth, unlike the often drier temperate karst areas.
Ah, so the sheer amount of rain compensates somewhat.
To an extent, for vegetation, yes. However, even in these lush tropical karst settings, finding reliable surface water sources for drinking or irrigation can still be a major challenge. So settlements tend to remain scattered, maybe clustered around resurgence springs or areas with deeper soil pockets, and the overall population density is typically lower than in adjacent non-karst areas that have conventional river systems.
It makes sense. You absolutely need to be able to access water reliably. If it's all rushing underground, that's a fundamental obstacle for large-scale human settlement and farming, unless you can dig very deep wells or happen to live right by a major resurgence point.
Precisely.
But despite these challenges of living directly on the rock for farming or settlement, are there valuable resources within the rock itself? Does limestone geology offer any economic opportunities or industries?
Yes, definitely. The rock itself can be quite valuable. The source mentions, for instance, that lead mineral deposits are sometimes found associated with limestone formations.
Lead, how does that happen?
Well, lead sulfide, the mineral galena, often occurs in veins. These are fractures or joints in the limestone that were later filled by hot, mineral-rich fluids moving through the rock over geological time. So, mining for lead has historically been an activity in some limestone areas.
Interesting. What else?
Limestone itself is, of course, a very widely used building material. Its durability, ease of working compared to some harder rocks, and local availability have made it a traditional choice for constructing houses, walls, churches, all sorts of structures in karst regions for centuries.
Yeah, you definitely see that. Beautiful old stone buildings and dry stone walls are very characteristic of limestone areas built directly from the local rock.
Absolutely. And perhaps most significantly in the modern industrial context, limestone is absolutely essential and extensively quarried for the cement industry.
For making cement, right?
It's the primary raw material in the production of Portland cement, which is fundamental to making concrete the most widely used construction material in the world. So limestone quarrying is a major industry in many karst regions globally.
And the source gives specific examples of quarries.
It does. It gives specific examples of important quarrying sites in West Malaysia, associated with those Perlis limestone hills we mentioned. It lists quarries in the Kledang Range, the Main Range, Panmalayan, and the Tasek Cement Works. This just highlights the economic importance of limestone as an industrial mineral.
So while the surface landscape presents challenges for farming and maybe dense settlement, the underlying rock itself is a crucial resource for construction and industry. It creates economic activity and employment in these regions. It's a bit of a geological paradox, isn't it?
It is, in a way, the very same rock properties, its solubility and jointing that make the surface difficult to live on in some ways, also make it host valuable mineral deposits, or be valuable itself as a raw material.
Okay, now we've talked a lot about limestone in general and karst features, but the source specifically makes a point of saying that chalk landforms are rather different from other types of limestone landscapes. What are the key distinctions the source draws for chalk areas?
Yes, the source explicitly makes that distinction, which is important. Now, like other limestones, chalk areas generally have little or no permanent surface drainage. The rock is porous, water sinks in quickly.
Okay, so drainage is similar.
And they also feature dry valleys, just like other karst areas. The source notes that in Britain, these dry valleys in chalk landscapes are often specifically called coombes.
Coombes. Right, a regional term for a dry valley, typically in chalk country like the South Downs in England.
Exactly. However, the typical topography, the overall shape of the land, is quite distinct. Unlike the often bleak, rugged, sometimes precipitous slopes you might find in harder, older limestones, chalk landforms usually present as low, gently rounded hills.
Soft and rolling.
Soft and rolling is a very good description. Think of the classic chalk downs of southern England or parts of northern France. Those smooth, undulating hills are very characteristic. Of course, you can get steep chalk cliffs right at the coast, like the famous White Cliffs of Dover. But inland, the landscape tends to be much gentler, much softer in profile.
Right. They definitely have that characteristic smooth rolling look. And what about the surface cover and how the land is used in these chalk areas? You mentioned sheep grazing earlier. Is that the main thing?
Sheep grazing is very important, yes. The source says chalk landscapes are often covered with that short, fine turf, which is excellent fodder for sheep. You'll also find areas of woodland, often beach hangers on the steeper slopes. But crucially, the source notes that arable farming, growing crops, is possible on chalk.
That seems surprising, doesn't it? Given the porosity and the general lack of surface water we've discussed for karst,
Yeah.
how is arable farming possible on chalk when it's often so difficult on other limestones?
That's a key difference. The source attributes this possibility mainly to the friable nature of chalk. Remember we said chalk is softer, more easily crumbled.
Yeah, friable means easily crumbled.
Right, so unlike harder limestones, which often present a solid, resistant rock surface with maybe only a thin, patchy soil layer on top, the friability of chalk allows it to break down more readily when weathered. This helps a more continuous and sometimes deeper soil layer to form, especially on the gentler slopes and in valley bottoms.
Ah, so the rock itself breaks down into soil more easily.
Exactly, and this soil, although it might still be relatively thin in places and well drained, is often sufficient to be plowed and cultivated for crops like barley or wheat. This is generally just not feasible on the hard limestone pavements or bare rocky surfaces you find in many other karst areas.
Got it. So the very softness and crumbliness of the chalk directly enables agriculture in a way that harder limestones typically do not. That's a really significant difference in terms of human land use potential, isn't it?
It absolutely is. It fundamentally changes the character of the landscape and how people can interact with it and make a living from it. And finally, the source makes one more important distinction about chalk compared to other limestones regarding the underground features.
What's that?
It states that swallow holes and the extensive underground cave networks, like those really complex systems we talked about earlier, are not generally as well developed in chalk as they are in other types of limestone.
Ah, so fewer big caves and sinkholes in chalk.
Typically, yes. While dissolution definitely still occurs in chalk and water drains underground, you generally don't find the same density of deep, dramatic sinkholes or the vast honeycombed cave systems that you see in regions like Kentucky or the Dinaric Alps or the Yorkshire Dales limestone. The subterranean development is usually much less expensive and less spectacular in chalk bedrock.
That's a crucial difference, too. So chalk still undergoes the basic karst dissolution process. It still has underground drainage and features like dry valleys, combes, but it usually doesn't develop those really deep, gaping holes or the massive, complex cave systems that are so characteristic of harder, perhaps more heavily jointed limestones.
Exactly right. The karst processes are certainly at work in chalk, but they often result in a softer, more rounded surface topography and less dramatic subterranean development compared to the classic, often more rugged karst landscape found in purer, harder, and perhaps more fractured limestone terrains.
Okay, wow. This has been a truly comprehensive deep dive, hasn't it?
Yeah.
We've traveled all the way from the microscopic composition of limestone and chalk these rocks derived from ancient sea life,
Right, built from shells and corals.
to the immense scale of landscapes shaped by the persistent, almost unseen power of slightly acidic rainwater dissolving calcium carbonate along natural weaknesses in the rock.
Mm-hmm. And we've explored that fascinating suite of surface features. This creates the vanishing streams, the ghost valleys, the giant's pavements of clints and grikes, the funnel-like sinkholes emerging into Doline and Uvalas, the vast flat-floored polyas, and even those dramatic gorges formed by collapsed underground passages.
It's quite a collection.
Mm-hmm.
And we've ventured into that hidden world beneath our feet, discovering how this exact same dissolution process carves out extensive networks of caves and caverns,
It's a subterranean labyrinth.
adorned with those spectacular, incredibly slow-growing mineral formations like stalactites hanging down, stalagmites growing up, and calcite pillars where they meet, all built up drop by drop over millennia.
It's like a hidden art gallery created by geology.
Totally. And we've seen where these regions are found across the globe, from their namesake in the Dinaric Alps to the UK, the US, France, Mexico, Jamaica, Malaysia, a truly global phenomenon under the right conditions.
And we've gained some real insight, I think, into how this unique geology presents both significant challenges for human settlement for traditional agriculture due to soil and water issues, but also provides vital resources like building stone and the raw material for cement supporting industry, and how it allows for different types of land use like grazing or even arable farming in those more friable chalk areas.
It really highlights how the ground beneath us isn't static at all. It's this dynamic entity, constantly being shaped by forces we often don't even notice day to day,
Hmm.
and how these deep geological processes profoundly influence the character of the landscape we see, and even impact where and how communities can develop and thrive.
It certainly makes you appreciate the incredible timescales involved in geology and the constant, subtle reshaping of the Earth's surface that's always ongoing.
Absolutely. And that brings me to a final thought, something to leave you, the listener, with.
Hmm.
If we understand now that water is constantly dissolving this rock, slowly eating away at it, carrying away that calcium carbonate in solution,
Mm.
what does that imply for the very existence of these features over truly vast geological timescales?
Mm.
Are the dramatic caves we explore, the intricate pavements we walk over, the deep sinkholes we marvel at, are they just temporary features? Are they just fleeting stages in an ongoing process of dissolution?
That's a deep question.
What might these incredible karst landscapes look like in the distant, distant future as this dissolution continues its relentless, slow work? Could parts of them, maybe entire hills or plateaus, simply dissolve away entirely over millions of years, leaving entirely different, perhaps much lower-lying landscapes behind?
It's a powerful reminder, isn't it, that even the most seemingly permanent geological features we see around us are ultimately part of a dynamic, ever-changing system. They're constantly in flux over timescales that just dwarf human perception. They are simultaneously ancient, yet perhaps also ephemeral in the grand scheme of Earth history.
Ancient and ephemeral. A compelling thought to maybe carry with you next time you see a rocky hillside or explore a cave or simply consider the ground beneath your feet. Thanks for joining us for this deep dive into the fascinating world of karst.